of all, I want to thank the organizers for giving me the opportunity to speak here. It's the last talk of the conference, and I will make it very, very short and very, very easy. So I'm going to talk about this short note we had. It is very much related to what Vladislav told you. It's related on to, okay, we had the question, you do this deformation of the cell affinity algebra, and you want to make sure that, okay, your quasi-isomorphism of the cell affinity algebra ensures you that you also get the physically equivalent solutions. So this is what we did. Oh, this is okay. We wanted to explicitly convince us of this fact. So we explicitly computed this, and then if you go into what this morphism gives you, you can show in a sense what happens to the field equations, and I will show how this works out. So the outline, I'm going to recall some definitions, and then I'm going to go to what we did. The first definition I want to show is that of a quasi-isomorphism. So you heard a lot of definitions of what an L-infinity algebra is and stuff, and we're always working here in this symmetric picture. So if you have an L-infinity algebra, I mean, you have created a vector space, and you have a family of maps, and all these maps are of degree -1 here, and they're graded symmetric. And now you want a morphism between these, and this consists of, again, multilinear graded symmetric maps at n, and now they are constant degree 0. And the important thing, of course, is they have to satisfy this fundamental identity. So there's a lot of things going on, permutations and stuff that's not so important. The important point is that there is this fundamental relation. And it's just a morphism. If you want to get an quasi-isomorphism, of course, F1 has to be an isomorphism on the homology, which analyzes L-infinity algebras. So the next definition I want to recall is that of a Seiberg-Witten map, and I want to recall it from like how Seiberg-Witten did in the original paper, and they considered D-branes in a B-field background, in a big B-field background, because, okay, this. So they considered this, and they noted, okay, they can shift this B-field dependence by making the D-brane non-commutative into this non-commutivity parameter. So this theta goes like 1 over B, and B is big, it's a small parameter. Then you get a gauge theory on this D-brane, which formally very much looks like usual gauge theory, but on every product, you just put the star product. And what they had in their paper was a sort of regularization argument. So they said, okay, this non-commutative gauge theory has to be actually equivalent to what you usually get, usual gauge theory. So they asked, can I find a hat between this non-commutative gauge field and lambda hat, which is the non-commutative gauge parameter, if you wish, such that gauge orbits get mapped onto gauge orbits. And then you can show, you can look in the paper and look at the explicit map, and then you can try and do, okay, well, what about the closure they have, and then up to first order, you can easily derive this equation and try to derive it to all orders. We'll see that this will come out automatically. So the last definition I want to recall is like what Olaf presented as in the beginning of his talk, and also Vladislav presented. So how do you fit this gauge theory into an L-infinity algebra? This is, we're always working on a graded vector space, which consists of like a vector space of gauge parameters, which are just maps into the Lie algebra you have, fields, and sort of this last vector space field equations, and the degrees are shifted because I'm working in this symmetric definition. And then having this, you can build up your L-infinity algebra very much by describing the gauge variation in this form, gauge closure. So you can notice here that we are not considering any off-shell, only on-shell gauge closure. So gauge algebra will always be off-shell closed. And the field equations, as you heard in Lorenzo's talk right now, just the Moroccan equations of the L-infinity algebra. And you also get the covariance of the field equations in this form. So what you do with this, you go and set up, okay, I have these two L-infinity algebras, which underlie these two classification theories, and now you suppose you have a Seiberg-Witten map. And then you can be sure that this can be recast in a form like Fn, that just creates symmetric maps at degree 0, so they do not satisfy anything so far. And why can you do it? Okay, this is just by a head of A can be an arbitrary nonlinear function on A, and you can for sure recast it in this form, right? Also for parameter, we can do this. And now you have this equation of motion vector space, and now you can say, okay, I want to relate elements in this too, and I can answer it like this. Plug this in. So you do now the Seiberg-Witten map, gauge orbits and gauge orbits. Okay, what you find is that this equation is actually exactly equivalent to these Fn to satisfy this morphin equation I showed before, on inputs lambda and an arbitrary amount of fields, but they do so only on shard. When you do this computation, you shift these parameters, these inputs around, you see that somehow the equation of motion built up, and if you set them to 0, this holds. And now you can somehow revert the logic and look, okay, what does this morphin's equations, what do they give me? And now you can do, okay, I plug in 2 gauge parameters and an arbitrary amount of fields, and you see, okay, this equation which you had for the original Seiberg-Witten map, like returning to the first order, you can show that this then holds to all orders. This may look a bit strange because here are these correction terms, but if you consider non-commutative gauge theory, you consider non-commutative U1, you will see that here this will be abelian, so this term will be just 0, but this term, this is non-abelian, and this will be present, so for sure there has to be corrections. The corrections turn out to be exactly this. And now the next equation is, okay, the field equations map onto each other, and this is true, and as you know, this is like the standard fact that if you have the quasi-isomorphism, this relates not with Petan elements and all Petan elements. And if you plug in parameter like thing of the equation of motion space and an arbitrary amount of fields, you see, okay, that this covariance of the field equations also gets translated in the right way. But these equations only hold on shell, so in all of this you have to set the equations of motion to 0. These equations hold in this form. So this is what I want to say. Thanks for your attention.
Any questions from the panelists? No? Okay, everyone wants to wrap up.
Before everybody leaves, let me just briefly say thanks to all the participants for attending and contributing to this, what I think was a very nice meeting.